In this lecture, we'll talk about the joy of infinity. So let's start with the question, is infinity a number? Technically, it's not. It's treated as if it's a concept that's something that's larger than any number. Technically, of course, there is no largest number, right? Because if you thought you found one, then you could add one to it and you'd have an even larger number. So even infinity is, but it's treated as something that's bigger than any other number, but it is itself not a number. Sort of reminds me of the song, Infinity Bottles of Beer on the Wall. You know, infinity bottles of beer, if one of those bottles should happen to fall. Infinity bottles of beer on the wall, right? You still have an infinite number of beer bottles. Infinity is something that is approached rather than reached. Sounds a little vague, I understand. If you look at the number line, then as you go way to the right on your number line, you're approaching infinity. It means you're going farther and farther and farther than any number that you ask for. Sometimes, though, we do treat infinity as a number. For instance, if somebody said, well, what do you get when you add up all the positive numbers? 1 plus 2 plus 3 plus 4 plus 5, and so on and so on and so on. You'd say, well, we'll say that equals infinity. And what that literally means, first of all, some mathematicians might even slap me on the wrist for saying it equals infinity, because then I'm using it as a number. They might put an arrow instead of an equals and say it goes to infinity. But I'm comfortable with saying it equals infinity. And what that means to me is that it's larger than any number that you ask for. That is, will that sum eventually be bigger than a million? Yes. Bigger than a trillion? Yes. Bigger than a Google? Yes. Any number you ask for, that sum will eventually exceed and stay above that number. That's what it means for the sum to go to infinity. And though it doesn't get as much attention, the cousin of infinity, sitting way the other end of the real line, is negative infinity, right? If you said, what's 0 minus 1, minus 2, minus 3, minus 4, for example, well that sum of negative numbers gets smaller and smaller than any negative number you ask for, and that's what it means to say that sum is negative infinity, okay? As a mathematical convenience, we will sometimes say things like 1 divided by infinity is 0. And that makes sense because if I take 1 and divide it by bigger and bigger and bigger and bigger numbers, by a million, a billion, a trillion, and so on, then that quotient gets closer and closer and closer to 0. You could even say that 1 divided by negative infinity is 0, right? Because if you take 1 over negative a million, 1 over negative a billion, 1 over negative a trillion, that gets closer and closer to 0. On the other hand, we always say that we are never allowed to divide by 0, okay? So you wouldn't say that 1 divided by 0 is infinity. And the real reason you don't allow that is because should 1 over 0 be infinity? Or should it be negative infinity, right? I mean, if you take 1 divided by a really, really, really tiny positive number, well, yeah, that's going to be some really, really big positive answer. But if you take 1 divided by a really tiny, tiny, tiny negative number, that's going to be a really big negative number. So as we get closer and closer to 0, if you get closer and closer to 0 from the right, yeah, you're going to infinity. But if you're going closer and closer to 0 from the left, you're going to negative infinity. And so that's why we don't define 1 over 0. We don't define it to be infinity. We don't define it to be negative infinity. We just let it be undefined. On the other hand, there are some infinite sums that add to things besides infinity. For instance, you could take 1 plus a half plus a quarter plus an eighth plus a 16th. That turns out to equal 2. And 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial and so on, that adds up to the number e. So just because we have an infinite sum doesn't necessarily mean we're going to get infinity as our answer. We'll see more of that in our next lecture on infinite sums. In this lecture, we're going to concentrate more at using infinity, rather than using it as a number-like object, we're going to use it as a size, okay? Mathematicians say that the size of a set, sometimes they'll use the word cardinality instead. I'll be less formal and say the size of a set S. And we denote that by putting absolute value symbols around the set S, is the number of elements in the set. So for instance, the size of the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is 10. Okay, so the size of that set is 10. Whereas the size of the set 2, 4, 6, 8, 10, since it has 5 elements, and the size of that set is 5. On the other hand, if I said, well, what's the size of the set of all the positive integers, 1, 2, 3, 4, 5, and beyond, because that set has infinitely many elements, we'll say the size of that set is infinity. Okay? And the size of the set of all even numbers, 2, 4, 6, 8, 10, 12, dot, 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 the size of that set is infinity. How many positive rational numbers are there, right? The set of all fractions. Well, there are more fractions than there are integers, right? So you'd say, well, there are an infinite number of those as well. If you look at the set of real numbers between 0 and 1, so you can capture that tiny interval in your hand, but between 0 and 1, there are infinitely many real numbers. So we say the size of that is infinity. But as we will see in this lecture, not all of those infinities are the same. Some infinities, as we will see, are more infinite than others. So prepare your brains for this, because this is going to be fun. Now, the way it's easy to count a finite set, right? I mean, if there are 5 students in my class, I can count them. 1, 2, 3, 4, 5. The size of the set of students is 5. But when you compare infinite sets, it gets a little bit trickier. Let's begin with a thought experiment. Okay, suppose I walk into a class and I see that every chair in the class is occupied by a student. Okay, there are no empty chairs in the class. And I don't have, and no students are standing, okay? Every student is sitting in a chair, and I don't have 2 students sitting in one chair, and I don't have 1 student with their legs across 2 chairs, okay? It's just the normal situation. Every student's in a chair, every chair has a student. Then I could go into that room and conclude that there are as many students as there are chairs. I might not know how many students, I might not know how many chairs, but I would know that there were an equal number of students as chairs. We call this a 1-to-1 correspondence. For every student, we can assign a chair. For every chair, we can assign a student. They can be paired up, okay? So if you want to use this to say compare the set of positive odd numbers with the set of positive even numbers, okay? Not only are there an infinite number of both of those objects, they have the same order of infinity because we can pair them up. That is, 1 can hold hands with 2, 3 can hold hands with 4, 5 can hold hands with 6, 7 can hold hands with 8. For every odd number, we can find a corresponding even number, and every even number holds hands with an odd number. So those sets, we would say, they're infinite, and we would say that they have the same size. Okay? Here's another example. Okay, I'm sure you have no qualms saying the size of the set of even numbers is the same as the size of the set of odd numbers. Here's where it gets a little trickier. How about the size of the set of all of the positive integers, 1, 2, 3, 4, 5, 6, and beyond, and all of the positive even integers, 2, 4, 6, 8, 10, 12, and beyond? Which set is bigger? Okay? Now, I hear a few answers coming out of you. One is, well, they're both infinite, so they have the same size. Not quite. Or you might say, oh, well, the first one is bigger than the other because there are more, 1, 2, 3, 4, 5, 6, there are more positive integers than there are positive even integers, so the size of the first set is bigger than the size of the second set. Well, that's not quite right either. I claim that those two sets do have the same size. And it's not just because they are infinite, it's because I can pair them up. I can give, just like I could give the students and chairs a one-to-one correspondence, I can give these sets a one-to-one correspondence. Namely, 1 is paired up with 2, 2 is paired up with 4, 3 is paired up with 6, 4 is paired up with 8, and so on. So both of those sets have the same size, not because they're both infinite, but because they can be put in one-to-one correspondence with each other. Mathematicians say that any set that can be paired up with the positive integers is called countable, because we could essentially list all of them just by counting. 2, 4, 6, 8, 10, 12, 14, 16. Eventually we will hit every even number. When will we hit the 2 millionth positive number? When we say our millionth number, that will be the 2 millionth positive number. An infinite set is, another way of saying that an infinite set is countable is if it can be listed with no infinite gaps. For example, let's look at the set of all of the integers, not just the positive ones, but the positive ones, the negative ones, and 0. Okay? I claim that that set is countable. It can be put in one-to-one correspondence with the integers, with the positive integers, because we can list them all out with no infinite gaps. We can say 0, 1, negative 1, 2, negative 2, 3, negative 3, 4, negative 4, 5, negative 5. Eventually, I will reach every positive and every negative number. That is a legal way of listing all of the integers. You would not be able to say, well, couldn't we have listed them by first listing out the positive numbers and then listing out the negative numbers? Couldn't we go 0, 1, 2, 3, 4, 5, 6, and so on and so on and so on, and then when we're through with that, negative 1, negative 2, negative 3? That's not legal because you'd never be through with your first step. That would have an infinite gap in the middle. So a set is called countable if it can be counted, if it can be listed, if it can be put into one-to-one correspondence with the positive integers. These ideas sound a little strange, and they were popularized, well, maybe popularized is the wrong word. They were invented by the German mathematician Georg Cantor. Popularized is a bad word to use because the notions that you're going to learn in this lecture were highly unintuitive. And it took mathematicians really decades for them to come to grips with them and agree that this really was legitimate mathematics. Nowadays, mathematicians can't live without these concepts. And we're expecting you to at least be familiar with them. Maybe they won't make complete sense to you in this 30-minute lecture, something that took mathematicians decades before they were willing to accept. So if some of this sounds a little strange to you, you're not alone. Okay, now let's look at a larger set of numbers, the set of fractions. Okay, so all the positive fractions, like 1 over 2, 3 over 7, 29 over 14. Those are the positive fractions. And my question is, though of course there are an infinite number of them, are they countable? Can you somehow list out all the fractions? Do they have the same size as the set of integers, the set of positive integers? Those have the same size. So do the set of fractions have the same size as the set of integers? Well, let's see. You might try listing them out row by row, but that would have infinite gaps. On the other hand, you can list the fractions in a more clever way by listing them out diagonally. Okay, so we have 1, then 2, then 1/2. 3, 2 over 2, 1 over 3, 4, 3 over 2, 2 over 3, 1 over 4. You know, those fractions whose numerators and denominators add up to 3, 4, 5, 6, and so on. In that way, you can list all of the fractions. So, in fact, the set of rational numbers is countable. It has the same size as the set of positive integers. At this point, you might be asking, well, maybe all sets are countable. Maybe every set, maybe all infinities really are the same. Maybe every set can, if you're diligent enough, be listed. Okay, let's come up with a set that is not countable. It's the set of real numbers, right? The set of let's in fact, I'll look at a really tiny set. The set of real numbers between 0 and 1. I claim that that set of numbers, not only are there infinitely many real numbers in that interval, there are uncountably many real numbers in that interval. And here's the proof, okay? It's a proof by contradiction. I claim that no matter how clever you are not going to be able to list out all of the real numbers. You're not even going to be able to give me a strategy for listing out all of the real numbers. And here is the proof by contradiction. Suppose you come up to me and you say, oh, Professor Benjamin, I have found it. I have a list of all the real numbers. And I say, really? Tell me how it goes. You say, okay, well, the first number on the list is, I'm just making up these numbers here. Let's say it's 0.3141596, Let's say it was pi over 10. Okay. And the second number is 0.12121212. And the third number is 0.500000. And the fourth one is 0.61803339. Okay, got it. Got a whole list of your favorite real numbers, all there. I claim, wait, stop here. I can find a real number, x, that is not on your list. And here's how I'm going to do it. I'm going to use your list to create a real number that can't be on your list. Here's what I'm going to do. I'm going to look at your first number, okay, pi over 10 there. I'm going to look at the first digit of the first number. That would be 3. And I'm going to change that. Let's say I'll change that number to 4. I'll add 1 to it. And then on the second digit of your second number, which is 2 in this case, I'll change that. I'll maybe make that I'll add 1 to that. I'll make that a 3. Okay? And then in the third digit of your third number, I'll make anything different. I'll make it a 1, a 7, whatever, anything but 0. And in the fourth digit of your fourth number, I'll make that different. Okay? And so on and so on and so on. And then I'm going to, in that way, create a number that is not on your list. Okay? So for instance, I've started creating number 0.4311, and it keeps on going. Now, how do I know that that number is not on your list? Well, could this number be the millionth number on the list? No. Why not? Because it will have a different digit in the millionth digit past the decimal point, right? The millionth number on the list has a different digit than my number. So the number I've created, it can't be the first number on the list, it won't be the second number on the list, it won't be the millionth number on the list, it is not on your list. So no matter how clever you are, any list that you create will not contain all the numbers, right? We know that the positive integers, the 1, 2, 3, 4, 5, that set is countable. The set of real numbers between 0 and 1, though it's infinite, it's not countable. There's no way of pairing up the real numbers and the positive integers. Another way of saying that is if I walked into a classroom and it had chairs numbered 1, 2, 3, 4, 5, 6, 7, 8, and so on, if the positive and negative numbers walked into the room, we could find everyone a chair. If the positive and negative numbers and all the fractions entered a room, we could find everybody a chair. But if the real numbers all walked into the room, even the real numbers living between 0 and 1, there won't be enough chairs for all of those real numbers, okay? And they'll get pretty upset. You might say they'll get irrational, but let's not go there. Anyway, we have a we now need to come up with different notation to represent these two different levels of infinity. So for the size of the positive integers, we denote that by the Hebrew letter Aleph. It's called Aleph 0 by most mathematicians as the size of the positive numbers. And anything that can be put into correspondence with the positive numbers, any countable set, has a size or cardinality of Aleph 0 or Aleph naught. The set of real numbers between 0 and 1 has a bigger level of infinity, and mathematicians usually denote that level of infinity by the letter C, where C stands for the word continuum. Now, the next question is, can we find a set that is bigger than C? Can we find a set that has more stuff in it than the set of numbers between 0 and 1 that cannot be put into one-to-one correspondence with the real numbers between 0 and 1? Well, the most natural thing to try is, well, how about looking at the real numbers between 0 and 2? Maybe there's twice as much stuff in that interval as there is in that interval. Both of them are infinite sets, but there is an elementary way to pair up the numbers between 0 and 1 and the numbers between 0 and 2. Take a look at this triangle. And inside this triangle we have a segment of length 1, and at the base we have a segment of length 2, and at the top of the triangle we have a little laser beam, and that laser beam connects for every point between 0 and 1, it's connecting it with another point between 0 and 2. It's a simple picture, but it's really kind of intriguing. It shows that we have as much stuff for every point in the first interval. We can pair it up with a point in the second interval. All we're really looking at, maybe this is a simpler way, is we're looking at the function y equals 2x. So starting from the x-axis from 0 to 1 and the y-axis from 0 to 2, look at that line y equals 2x. Do you see that for every point on the x-axis, that's associated with a point on the y-axis by way of that function y equals 2x? So that shows that the size of the real numbers between 0 and 2 is the same as the size of the real numbers between 0 and 1. In other words, it still has size C. All right, well, let's look at a bigger set. How about the size of the set of all real numbers? Not just between 0 and 1, not just between 0 and 2, but from, dare I say, negative infinity to positive infinity, right? Look at all the set of real numbers. Maybe that's a bigger set in terms of its size than the set between 0 and 1. But as long as I draw any function that more or less goes from negative infinity to positive infinity in an increasing way, I've drawn here a trigonometric function. Y equals the tangent of pi times x minus a half. But that's just a formulaic way of writing this little function that creates a one-to-one correspondence. Between every number from 0 to 1, we can get every real number, positive, negative, 0, it's all in there. So that says that the size of the set of real numbers is still the same as the size of the set of real numbers between 0 and 1. It still has a size of C. So let's try and find a set that has a size that's even bigger than C. Well, the next thing to try, even Cantor tried this, thought that this'll do it. Let's look at the set of all pairs of real numbers. Let's look in the plane, okay? The set of points that live inside the unit square. Yeah, well, if there are an infinite number of points between 0 and 1, there's certainly an infinite number of points in the square, 0, 1 going horizontally and from 0 to 1 going vertically. And yet, amazingly, even this set can be put in one-to-one correspondence with the set of real numbers between 0 and 1. And I'll illustrate the way of doing it by an example. Let's say x was 0. The digits R1, R3, R5, R7, ... and y was 0. R2, R4, R6, R8, ... Okay, so there's an ordered pair that lives inside that square. We're going to associate it with the real number 0.R1, R2, R3, R4, R5, R6. For example, if you started with, let's say, the point 0. Let's say pi, 3141592.6, that's going to hold hands with the ordered pair 0.3452 ... Notice I'm taking every other digit starting with the 3, and 0.1196 ... I'm taking every other digit starting with the 1, and they are holding hands with each other. From any number on the left can be turned into a pair of numbers on the right. And for any pair of numbers on the right, I can turn that into a number on the left. So there are as many numbers of the first type as there are of the second type. In other words, the set of points inside of this unit square is the same as the set of all real numbers between 0 and 1. To put that another way, the size of the set that's called R2, the size of the set of all pairs of real numbers, is C. The size of the set of all triples of real numbers is C. The size of the set of all 4 tuples of numbers, 5 tuples of numbers is C. So we still haven't found a set so far that has a size bigger than the size of the set of real numbers. But here is a larger set. I won't prove it to you now, but I'll just tell you, here's a larger set. The set of all curves in the plane is a set that is strictly larger than C. That is, if you wanted to try and pair up every curve in the plane and assign it a real number, you won't be able to do it. There will be too many curves than there are real numbers to assign it. Actually, there's a little bit more you can say, and we won't go into the proof of this, but it's a real intriguing one. That the set of all subsets of real numbers is bigger than the set of real numbers. Okay, so the set of real numbers is infinite. The set of all subsets of real numbers, like here's a subset of real numbers, 1, 2, 3, 4, ... That's a set of real numbers. The set square root of 2 and 27. That's a set of real numbers. The set pi squared, pi cubed, that's a set of real numbers. How many ways can you create a set or a subset of real numbers? There are infinitely many ways. In fact, so many infinitely many ways that you cannot pair up the real numbers with the set of all subsets of real numbers. So we have a higher order of infinity there. As it turns out, by the way, as a piece of trivia, the set of all subsets of integers has the same order of infinity as the size of the set of real numbers. So let me recap here. What we have shown is that a set is infinite if the size of that set exceeds any given number. The set of integers is countable because we can list them, 0, 1, -1, 2, -2, 3, -3, as are the sets of rational numbers. They have a size that's called aleph naught. The real numbers are uncountable, and they have size C, and there are uncountably many real numbers. They cannot be paired up with the integers. And lastly, there are infinitely many levels of infinity. Now, at this point you say, infinitely many? How infinite? Is it countably infinite? Uncountably infinite? Let me end with a word of warning. Don't think about these problems too hard, because if you do, you might end up going depressed, just like George Cantor did at the end of his life. But think about it a little bit, and I think you'll be intrigued. Thank you.